So it should be recorded. Okay, good. So now this during this stage of the presentation, I will go through some material results that I have collected in my previous investigations to demonstrate actually the fatigue performance of composites. I will talk about the material here. It's a first material that I'm discussing. It's a glass fiber reinforced polymer, GFRP, multi-directional composite laminate. Actually, this is work that I've done when I was a PhD student. This is 25 years old. The material system is a glass polyester laminate with this stacking sequence that you can see here. So it's a building block used for wind turbine rotor blades with 0, plus, minus 45 and 90 degrees layers placed in certain configurations. And then we cut specimens at different directions, 0, 15, 30, and so on. And we performed a lot of quasi-static and fatigue experiments. In total, 350 specimens were performed in this investigation. What was the objective? You remember we discussed before about the objectives. Well, what is the expected result? And in my case, the expected result was to create a database that was enough for helping developing a new fatigue failure criterion for multi-axial stress states, and also validate it for constant amplitude fatigue and for variable amplitude fatigue. So to do this, I had to create all this. So this is my test matrix. This is how we start testing. We set the objective. We have an objective. And then we start thinking and saying, okay, to achieve this objective, what do I need? And what I need is, in this case, what I need is to perform quasi-static testing, to create a table with my properties in quasi-static loading. You see also here that I have tests at 1 millimeter per second and tests at 40 kilonewton per second. So these are the different loading rates that correspond to the standard testing and correspond to the testing rate that is related to the fatigue testing. Then I have constant amplitude experiments, because with this I can investigate the material performance at different ratios, at different angles, and develop my tools for the fatigue life prediction. And then what you see here with the variable amplitude loading is experimental results that have been used, of course, to investigate the material performance under these loading conditions, but also they were used for the validation of the developed modeling techniques. At the end, if you want to see also a number of cycles, it's something like 140 million fatigue cycles. This means more or less a year of testing, continuous testing in the lab. So the way of preparing of laminates was more or less like that. It's a visualization of what we were discussing before. We have a laminate with 0, plus, minus 45 2 times, and 0 layers, plies, and we cut specimens at different orientations. And the reason for this was that when you have specimens off axis, we call these specimens that are tested on axis with the fibers along the loading direction, and we have specimens that are tested off axis. So when you have off axis specimens, you have a different, depending on the off axis angle, you have a different combination of a plane stress condition. So with these plates that we manufacture, we created specimens. Why this geometry? Is exactly because we discussed before that this geometry is recommended, is not imposed, but recommended by standards. In this case was the ASTM standard for having reproducible results. And then we use also an anti-buckling device. I don't know if you are familiar with these devices, but are devices, usually metallic devices, that are used to constrain the specimen, to confine the specimen, if you want to say it like that, and avoid buckling during loading when we have a compressive loading applied on it. It's very significant to have it because our materials, composite materials, are slender. They are usually long and thin. And when, of course, you can imagine when you load something that is long and thin in compression, it tends to buckle. As you will see later on in this presentation, this anti-buckling device, although it helps avoiding this buckling of the material, it causes also other effects. Sometimes it is too much confining, and it does not allow the material to behave as it would be behaving in compression if it wouldn't be constrained like that. Another problem that we had with this anti-buckling device is that due to this enclosure of the specimen in the device, when we were performing fatigue testing, in some cases, we measured very high temperatures in the specimen. And this, as we've seen before, it's not a good sign for the specimen itself. So the first results, as we said, the quasi-static results, allow to develop this kind of table where we have the UTS is the ultimate tensile stress, and UCS is the ultimate compressive stress of the material, so the stress at failure or the strength of the material at different orientations. You remember that we cut specimens at different orientations. And you see that there is this normal drop. They follow a kind of exponential drop with as a function of the angle that we cut the specimen. We use these material properties to do modeling. And for modeling, we also need the properties at shear. And in this case, we used as a shear strength this one that can be calculated by assuming the strength at 45 degrees in tension and strength at 45 degrees in compression divided by 2.2. Does this remind you anything related to metals? The person that asked about metals before?
No, sir.
No? What is the shear strength of the metal, of steel? If you know can you tell me the shear strength of steel if you know the tensile strength of steel?
It is around 50 to 60% of tensile strength.
Yes. So what do you see here? So your tensile strength here is
Yes.
140, and here so I have a different differential between the tensile and the compressive stress, but more or less my shear is half of the tensile strength. So you see that in composites, this is again valid as it was for metals. And why it is valid? Because in composites you have the same physics or mechanics as what you have with metals. In metals, this is what you have. No? This is the typical, this is not related to material, by the way. This is the transformation of stresses, and the maximum in-plane shear stress is given by this condition. And in the case where you have only uniaxial loading, it means that this is 0 and this is 0. So your in-plane maximum stress is more or less half, because the 2 goes out with the square root, is more or less half of your tensile strength. So it's the same case, metals and composites in this region, because there we talk about mechanics, we talk about physics. We're not talking about material. So coming back to this, we can we know that we can use this here. You see, it's not exactly 2 because of the differential between the two, the tensile and the compressive strength of the material. So after the quasi-static testing, we did fatigue loading. And we did fatigue loading, if you remember, we did fatigue loading at different loading cases. We had reversed loading, and I'm now introducing again terminology. We discussed a bit yesterday, but we are now introducing more. We have reversed loading, which means we go from a zero mean stress, average stress, to a maximum stress, and then to the same value at a minimum stress, negative minimum. So this is a condition where we apply tension and compression fatigue to the specimen. And this is what we call the stress ratio. The stress ratio is the ratio between the minimum and the maximum. So here in this case, the stress ratio is -1. We can also have this orange spectrum here, which goes from 0 to a maximum value. And in this case, the stress ratio is 0 over something, which means that it is 0. And this is tensile loading, only tension to the material. There is also another case that we did where we went from 0 to minus something. So it is always a compressive loading. And in this case, the stress ratio is minus something, so minimum over maximum. And so it's minus something to 0, which means that the stress ratio here is infinite. And we had also cases where the stress ratio is defined by minimum to maximum, in this case from 0.5 to 1, which means that the stress ratio here is 0.5. And here again, we talk about a tensile fatigue loading. So we had all these different loading conditions at always the same frequency of 10 Hertz and at laboratory conditions, so controlled conditions in the laboratory. And of course, you can imagine that the necessity of this anti-buckling device was exactly there because of this testing. This testing condition is this testing condition, which applies loading that it is negative. So there we have compression, which means that we might have buckling. The same happens with this one, -1, which is this one. This one also has positive and negative values. So these negative loads on the specimen can also create buckling. So for these reasons, we use this anti-buckling device. So the results are given here. I will open all of these graphs to discuss. We have results for R equal 10, so compression. We have results for R equal 0.1 for tension, reverse loading, -1, and 0.5, which is only tensile loading at a higher mean stress. And this was there, this testing was there to investigate the mean stress effect. First of all, a very brief comment about this. R equal 10 and R equal to -1. Before we said that we can have also, I can go back to the previous slide. We can have testing that is with R equal 0 instead of 0.1. What is the difference between these two? For 0.1, instead of starting at 0, we start at a slightly higher value. And this is also valid for metals fatigue. It's not only related to composites. Why we prefer to start at this slightly higher value than starting at 0, both for tension and compression? Can someone comment on that? What is the reason for selecting R equal to 0.1 and R equal to 10 instead of selecting R equals 0 and R equals infinite. Who is involved with experiments in their work? Do we expect to have perfect tests when we ask the machine to go from load level A to load level B? Does the machine obey exactly at this request, or it does something else? How do machines work? Do you know how hydraulic machine, a servo hydraulic machine works? What is the control system?
That is mostly servo hydraulic, basically.
Yes. So what is the control system in a servo hydraulic machine? How do we call
Either
it? Terminology. Again, terminology. How do we call a servo the control system in a servo hydraulic machine?
They can control the flow basically through feedback, force feedback sensors basically.
We call we call it a closed loop system.
Closed loop system.
Exactly. Why a closed loop system? Because the machine gets the demand from our side and gives some output, and then if the output is not exactly the same as the demand, it does a correction with what we call the PID in this closed loop control system. It does a correction, and then the second time it gives a better result, and then the third time it gives a third better result, and so on. So it improves. That's why we call it a closed loop, because the testing conditions are improved every time that the machine does a trial and error, if you want, or an iterative process of improving the testing. So what might happen if we select our ratios that are equal to 0 or infinite, is that when we ask the machine to do tension testing, the machine does also apply some compressive loads that might be also very critical to the specimen, because as we said before, we have slender specimens that cannot sustain compressive loads. So this is what might happen when we select 0. That's why we select a bit higher than 0 to have this kind of safety there, that the machine, although it might do some overshoots in the loading, does not go from tension to compression. So above this is technical details for the testing. And then if we come to the results themselves, we see, of course, the effect of the off-axis angle. You know, what we've seen before. We'll draw here to avoid going back. For the quasi-static results, we had this kind of behavior with the angle theta, with the strength. And now you see also the fatigue strength of the material is following the same trend. From 0 to 90, we have better performance at 0, and the worst performance at 90 degrees. And you see this is the 90-degree specimen. This is the 0-degree specimen. And in all cases, check here, check here, check here, 90 degrees are the worst case scenarios, and 0 degrees are the best case scenarios. What we also see, if we compare in between the cases, we've seen that there is a kind of correspondence between these two. The tensile performance, you see it's around 90, where we have the maximum. It's around between 60 and 30, where we have most of the data. Between 60 and 30, we have most of the data. So, which means that the material behaves more or less the same in tension and compression. There is only a bit of improvement in the 0-degree specimens. I will come back to this later on. There is the effect of the anti-buckling device that we discussed before, that actually damage a bit more these specimens. But I will talk about this later on. And what we
ask one question here.
Yes.
The scatter is also more in 0 degree, or is it same? Like the scatter can be like same for other angles also.
The scatter is a bit more in this case for 0 degrees. Although you might be, how can I say, misled by the scale. Be careful when you read diagrams, because the scale here, you see this curve here for 45 degrees or 90 degrees is very flat. So the scatter that I see, if I check, for example, here, there is scatter between half. By the way, again, terminology, we call this a decade of life. From 10 to the power of 3 to 10 to the power of 4 is a decade of life. And for composites, again, coming back to the previous discussion, this is the difference also between composites fatigue and metals fatigue. In composites, we usually have more scatter for several reasons. Manufacturing defects, misalignment of fibers, and so on. There are a lot of reasons for this. We have more scatter than in metals. And here in composites fatigue, we more or less assume as acceptable results those that are in each stress level. This is one stress level, a second stress level, and so on. Each stress level shows less scatter than a decade of life. So in this case, here we are okay. Here we are okay. Here we are okay. Okay, doesn't mean that we are good, we are happy with that. There is a huge scatter, and you see here there is a big scatter. You can have specimens. What does it mean, a decade to life in this? You have specimens that failed at, so 10,000, 10 to the power 5 is 100,000. So specimens failed at 200,000 cycles, and specimens of the same load level that fail almost in 1 million cycles. This is 5 times more life in the same stress level. But this, according to the experimental evidence that we have for composite materials, this is assumed as an acceptable scatter. So coming back to your discussion, your question, I wouldn't say that that's more scatter in 0. It's more the scale that shows this scatter.
No, the reason I am asking is because in the fiber dominant properties, the effect of cutting in a slightly wrong angle, like not maybe perpendicular, and all those effects will be predominant.
Yes.
Rather than 50 degree and 45 degree.
Yes, I agree with you, but do not forget, and this is a point that we discussed yesterday. Do not forget, I'm going back, the laminate that we have here, and my 0 is not an actual UD. My 0 has 2 UD layers and 2 layers of plus minus 45 degrees.
Okay.
And this, why I said that this is a discussion that we did yesterday, that we said yesterday that we almost never, if I can say like that, we do not tend to use unidirectional composites with one fiber direction for structures, exactly to avoid these problems that you're mentioning. We try to homogenize a bit the material, to mix layers, so that we can consider effects that are not actually seen during the design. So what you see here, and we say even here in the static strength results, when we say with the angle theta, it's not the angle of the fibers, but it's the angle of the total laminate. So when we are at 45 degrees, we have fibers at 0, because the 45 degrees layers, when you rotate at 45 degrees, become layers with 0 and 90 degrees fabrics. Okay, so this is the basic discussion. What we've seen is more or less that the more damaging condition here was the R equal -1. And this happens because of the change between the tension and compression. It seems that this change between the tension and compression and the maximum, the highest amplitude that you have to apply to go from minus something to plus the same value was really critical for this material.
Especially for R equal to -1, any special care need to be taken apart from that anti-buckling device?
No. The only thing that you have to keep in mind for -1, for R -1, is that it has the highest amplitude. Right? You need to do a test that goes with the highest amplitude. And when you talk about, for example, the R equals 0.5, the amplitude is very low, because you are starting already at the high stress, at the high mean stress, and then you need to do a very, very low amplitude. If you think a bit of this definition of this R ratio equal to 1 is a creep test. And can you imagine this?
Yeah.
R ratio equal to 1 means that you are loading, you go to a certain value, and then you load there without amplitude. So this is a creep test. You go to a sigma max, and you stay there. And this is exactly the definition of R equal to 1. So in this sense, the creep testing can be considered as a sub category, if you like, of fatigue testing at a specific ratio. And there, depending on the frequency that you are using for your testing, I imagine you're testing at a certain level with a very, very, very minimum amplitude, very, very small. So you are 0.999 in terms of R ratio. And if you assume a certain frequency there, you can do a certain fatigue testing, which corresponds to a creep test. And you can then attribute this frequency that you have to the time that you spend, and you have exactly a creep test that is also correlated to your fatigue results. We'll see also later why this is important, why the creep information for the material is important when we talk about fatigue. So I'm coming back to the analysis of the results, and here is the summary where we saw the model parameters of a simple equation of the type of this one. Do you remember this equation? How did we call it, or where did we talk about this again yesterday? It's the equation that we said that has been introduced by Basquin in 1910, and it's the power law equation. It's a straight line on the logarithmic of number of cycles to the logarithm of stress, of cyclic stress plane. If we plot the data in this plane and we fit this equation, it's a straight line. So you see that even today we use the same equations like Basquin did 110, 20 years ago. And these equations are still valid today, because as we discussed also yesterday, they are valid for more or less any material. You can also use this equation for metals fatigue. Although there the standards are simplifying, and you usually take a linear plot but again, it's a linear plot in a logarithmic scale, no? So metals are using the same equations here. So what we can discuss on this table is, first of all, the slopes. Probably there is already there. Huh? Yep, okay, it was there. I don't have to draw. So the slope of the curve, which shows the rate of the damage development. For me, this is more important than the intercept, than these values here, the sigma 0. The slope of the curve shows the sensitivity of the material at this condition. And what we can see here is that, coming back to your comment, that 0.1 is more sensitive to fatigue loading because it shows more or less as an average, it shows the highest slope. While in certain cases, when we go off axis, we can see that -1 is really the worst case, where we have slopes that are reaching 0.1, which means 0.1 means this 1/k is 10. K is 10. In metals, again, you have values there. And in metals, the values are much higher. In metals, the values are even reaching 20. So this means that if we do a comparison of metals fatigue with composites fatigue, you have this behavior. So this is number of cycles, this is stress. You have this behavior for metals, and you have this behavior for composites. This is the main difference, if you want, on the level of the SN curve between metals and composites. Okay? So, and then we have this mean stress effect. I will again open these two. And the third one. If we plot together the specimens for 0 degrees, these are this first slide, this first photo figure shows all the specimens for 0 degrees at the different R ratios. This one is the specimens for 45 degrees at the different R ratios, and this one is the specimens for 90 degrees at the different R ratios. And you see here we plotted against sigma max and not against sigma alpha that we had before. And we can compare now the maximum, so the intercept and the slope of the curves. And you see, as we discussed before, that 0.1 is showing the highest slope than the others in the 0 degrees. And also when we compare to 45 degrees and 90 degrees, the material is quite critical for the cases that have been discussed before. So this is how we compare the mean stress effects, and then of course we have the ability to plot all this together in constant life diagrams. We will discuss about this in a few minutes. Huh? So if we come back to analyze the mean stress effect on axis specimens, we see that the failure is due mainly to fiber failure. And the reverse loading is the worst case. And the tensile loading is the best. You see that it is at the highest levels in the beginning, and it becomes worse when we go to very, very long lives. And this is relevant. The failure mode is relevant to the matrix cracks that we had in tension in static values, that finally the fatigue strength of the 0.1 becomes steeper, not stiffer, but steeper than that of the R equal to 10, to the compression loading. So when we go to off axis, you see that the failure is not anymore based on fiber failure, but it's mainly due to matrix failure in between the fibers, and there is also significant delamination in these cases. And as we said before, there is a peculiar behavior for the R equal 10, but we have reasons to believe that this is an artifact from the anti-buckling device. This is what I mentioned already before that we've seen that the anti-buckling device was confining the specimen more than what is needed and also causing a lot of temperature increase in the specimen during the testing. So if you want to see some results and solutions for this problem is to avoid having the anti-buckling device. It has been suggested several years ago. We had a big European project working on that, where we suggested to use short specimens instead of the anti-buckling device. And the idea is to use these short specimens means instead of the standardized specimens that are 25 centimeters long, we suggested to use specimens that had a free length. So the length that the specimen was outside the machine was only 30 millimeters. So very, very, very short. And here I have a video showing the behavior of this specimen in tension. You see how it fails in tension with, if I run it again. So I run, you see here initially damage, oops, sorry, I went further. So initially we see matrix cracks, the whitenings here, the lamination, and then failure of the fibers at the end. And there is also, this specimen has been defined, mainly has been introduced for compression. And here I will show you compression results of this specimen, proving that the testing is valid, because exactly you see that, you see that the failure is a compressive failure at 45 degrees. And this is exactly the way that a compressive failure should be when we don't have buckling. So we validated these specimens, and then we also perform fatigue testing with these specimens, and we've seen that they are very, very convenient for doing this kind of investigations and avoid having these anti-buckling cases. So when we go to the 90 degrees.
One question related to the geometry, what you just mentioned.
Mm-hmm.
So, as per ASTM static testing, there are some dimensions specified for the static testing. So for R is equal to 0.1 or like tensile kind of testing, we can use D3039, but for other like especially for compression and reverse loading, we should use similar to D3410 kind of specimen, like short specimen.
Again, there is a how can I say, it's the selection of the specimen is related a lot to the objectives of the testing. If the objective is to estimate material properties for design, then you have to follow the standards and follow exactly the recommendations there to estimate properties for design. If your objective is to compare the behavior of the specimen of the material at different conditions, then probably it's a good idea to use the same specimen for all conditions. Because we know also that the specimen type, and I will show later on, although it is recommended by the standards to use different specimens for several conditions, we've seen
that. The reason is because
sorry?
Fatigue, there is no, especially for fatigue, there is no standard available except the tensile testing. So the reason I'm asking is, shall we stick to the similar specimen? I am using the word similar, which we are having in static testing standards, basically. Mm-hmm. Like a short specimen for compression or tension testing.
Yes, the response is simple. You should not stick to the standards. You should question the standards, and I will show later on why. And there is also, for fatigue of composites, there is also a lot of discussion between groups. And there are groups especially from Denmark and the Netherlands, that they even prefer for unidirectional composite laminates to use a kind of dog bone specimens instead of the rectangular specimens that we are using. Because they believe that the stress concentration that is relieved by these dog bone specimens is improving the behavior. We've seen yesterday in a slide where I showed these specimens with the change in the cross section and the improvement that they claimed in this publication that they had. And I will show later today some results of adhesives where you can obviously see that the effect of the specimen type is significant, is very, very significant. Okay. So now continuing to this, if we go to the off-axis specimens at 90 degrees, we see a bit different behavior. The failure is clearly due to the matrix. We have this kind of configuration. We have matrix cracks in the matrix that when they happen, they lead the material to failure. So we have a lot of different in quasi-static loading. The material was similar to tension and compression, but in fatigue we have differences because there in fatigue we have a lot of matrix cracking that is accumulated during loading. You will see later on also a specimen at 90 degrees failed that showed a lot of matrix cracks in the layers and also a lot of delamination, so matrix cracks that propagated in between consecutive layers. So as we said, the observations that we do on the failure mode can support these arguments that we try to establish here. So how we visualize the mean stress effect. I will introduce this topic and then we can do this the second break. But for visualizing the mean stress effect, I mean, we can continue discussing on the level of the SN curves, but in the late years, but probably 50 last years, it's not the late years, the concept of the constant life diagram has been introduced, where the fatigue data can be plotted in the mean stress and amplitude plane to represent altogether the fatigue data independent of their ratio. And then we can plot so simply showing like that, we have the sigma m, sigma alpha plane, and we can plot the data for each fatigue curve as radial lines emanating from the origin. So each line can be reproduced by this simple equation. You see it's a line. Depending on the ratio, you have a different angle between the two axes. So constant life lines can be then derived. You have this constant life diagram, and constant life lines can be derived by connecting these SN curves. We have, I can go here, we have this SN curve for 0, we have this SN curve for -1, we have this SN curve for 10. So on this SN curve, we can come and select the point corresponding to 1,000 cycles. And we can go to this SN curve and select the point corresponding to 1,000 cycles. If we connect these points, then we have a constant life line corresponding to 1,000 cycles. When we connect to the next one, the same. So we can go then to 10,000 cycles. We can do the same. We can go to 1,000,000 cycles, and we can do the same. So this is how we create a constant life diagram. So constant life diagrams are visualized also in this figure on the right. They have different domains. We have the tension domain here, the compression domain here, and the mixed, if you want, domain, the compression tension or tension compression, depending on where we are. This is in this range is tension dominated. Here is compression dominated. The usefulness of a diagram of this type is to show, first of all, the material behavior with loading. If we have a diagram like this, the diagram that I plotted just before, shows that the material is not sensitive in tension or compression. It shows the same performance in tension and compression. if you have a diagram that it is like that, might be, but you have a diagram like this. This diagram, okay, let me clean. If you have a diagram like that, this diagram shows that your material is more performant, it's performing better in tension and less in compression. And the opposite also, if you have a diagram like this, it means that your material behaves better in compression than in tension. So like that, you see very easily, if you plot all the results on the SM and S alpha, so stress, mean stress and amplitude plane, you can have a very easy visualization of the performance of the material. How you do this is different. I mean, to connect this, you can use several methods that exist now, and this is now related to the modeling. First we have the visualization of the material, and then we can model the behavior. And why we need to model the behavior? Because then, if we have a model that tells me that from this line to this line I can go with a linear interpolation, then I can come and apply the model and estimate the SN curve at a R ratio that is not known. Here it might be a ratio of 0. or minus 0.4, for example. And we don't have any experimental for this, but we can estimate this SN curve by using the CLD, the constant life diagram. And this is the validity of the constant life diagrams. There are methods for visualize the fatigue performance and methods also that allow to estimate, to calculate additional SN curves, so fatigue data, for conditions that we haven't seen yet. And as you will see tomorrow when we'll talk about fatigue life prediction, this is very important, especially when we try to estimate the lifetime of a material under a block loading and variable amplitude loading. So the constant life diagrams for our case, for our material, are shown here. And immediately we can see what we said before, that the material is better in tension, the R equals 0.1. So it's a bit better performance than -1 and 10. So it's better in tension than in compression, in on axis. When we go to 45 degrees, the material becomes better in compression instead of tension. And this shows the material anisotropy. We also see here that the material cannot be, the behavior of the material cannot be simulated by the Goodman diagram. The dashed lines here correspond to the Goodman diagram. The Goodman diagram is not able to simulate the material behavior at very many cases. The same here, the same when we go to off-axis, Goodman diagram would be like that, which means that it is not conservative at all, which means that if we use Goodman diagram in this case to design a structure, the structure will fail because of this, the same here. The structure will fail because we create an envelope, a safety envelope for the material, which is not related to the performance of the material itself. So we'll see more about SN curves and CLDs in the following lectures, and also discussing about the modeling of this. So we also did, if you remember, interrupted fatigue loading. And to discuss this, I would suggest interrupting our lecture again for a couple of minutes and coming back with the third and last part later on. If
Yes, interruption is needed for relaxation. So it may improve the fatigue life of the participants also. Otherwise they'll fail so soon.
Exactly. Okay, so 10 minutes break and we come back.
Yeah. So
Okay.
we can keep connected, and then the speaker will take a maybe 5, 12, 10 minutes break.